Okay, let's come to the final last chapters. We have already talked about 910. That was the deadbeat version of my idea with the degree of 4. Just really not theoretically nice. We can show that you can design this type of controller for any degree. So note just this page. I shift this page into this window, and then you can see really, yeah, the 4th order degree transfer function of FFZ contains 8 unknowns. So 8 unknowns. No, you have sorry. The A's and B's are not the unknowns. The unknown values are the X values of the model in the future. We want to have the Y value of the controller, and you see here are in this list are the unknowns we can calculate now with the measured values, old values of input and output, with given process A's and B's. You can calculate the Y of K, the 3 further controller output values, and the predicted 3 future model output values in one step. So you need just an inverse calculation of a matrix like this. This can be inverted. You see this contains no measurement value, so you can do this inversion in a step previous to the start of the controller. You have just calculate these expressions in each step, and then you can calculate all these values. This is programmed in WinDF C#. I have programmed it, tested it, really it runs, but the model identification of a 4th order model is really not not really usable. So don't spend too many times on this. I have done this experiment with a hardware simulator with 4 PT1 model with time constants 1, 330 milliseconds, 50 milliseconds, 10 milliseconds, and a sampling time I think of 10 milliseconds. And I look, sampling time 100 milliseconds. You see here the different controllers. My deadbeat version is ready after 4 steps. Yeah, and the PID is much slower. The orientation controller is also slower. So you see, without limit, the red curve is valid. With a 10-volt limit, the green curve is limit. So my controller version works also including the controller output limitation. Okay, in 911 is an added chapter with the Smith predictor. So we have talked about this, we have used this, I have explained it. So I skip this and come to a really new chapter. This is a discussion, comparison of the original PFC version with the PI. So we have seen that the PFC has a property that the disturbance is completely compensated, so there must be an integrator. But if you look on this expression with which you calculate the output value of the controller, we really cannot see the integration. So I have analyzed this. That's my work on this controller. That's not a Richelieu result. It's my result. I have analyzed the PFC with a PT1 process in a following way, and the result is astonishing because the PFC really behaves like a PI. Okay, wait for this. I want to show this step by step because this is a rather nice way to try to understand the PFC version. So 9/11 already done. So what we now do is that the analysis analysis. Okay, analysis of PFC controller. Okay, in the paper you see that the calculation of the output of the controller y of k comes with a constant which depends on some parameters but is constant, multiplied with the desired value minus the actual value. That's a control difference, well known as a control difference. But that's not all. There is another coefficient, and this coefficient, this part of this expression is 1 over km, called A1, times what? Times the model output xm of k. Okay, to understand this, we can say the first part is very simple. That exactly what a P controller does. But what is this? Yeah, the second part is not easy to understand because I will show you that the second part is the integrator. Why is this an integrator? To understand this, I draw now a signal block diagram of this situation. Yeah, we have a control loop with a desired value input. That's standard. Then we have a process, and we talk a very simple case. We talk about the very simple PT1 process. This is a real process in our situation. The output is x of k. We sample this, but this is coming out of the sensor of my process, and we can close this loop in that way that we can say, okay, here, this output of the summing point with this minus sign, this is a control difference, and this is multiplied with a P controller with the gain A sub O. Okay, and this output is the first part of my calculation, but that's not all. There's a second part. So I can call this y1. Yeah, y1. So this is y1. The output is y1. And then we have an addition. The signal, the sum of this signal then is y of k. Okay. The question is, how can we draw now this part, the second part? This xm of k is an output of a PT1 model, and the input of the PT1 model is my y of k. So we can say, okay, this y of k signal goes into a second PT1, and the second PT1 is my model. Okay, the case and T of both model and real process should be the same. Yeah? Otherwise, this doesn't work properly. And the output of the model here, this is the signal we can say is xm of k. This is multiplied with a gain factor. Gain factor is 1 over kn. 1 over kn. So, and note there is a plus sign. Yeah, a plus sign. So this is a feedback situation with a positive sign, so a positive feedback. Can you remember what happens if I have a positive feedback in this situation? I have used this, or Mr. Rischerle has used this in a similar way here in this situation. Note, we have calculated this part here, this part with this number. This was a PI. This exactly gives a PI behavior. So as you see, a PT1 model feedback with a positive sign. This is my integrator. I show you this with equations. We want to have some values where we can say, okay, what is this? Total, is this really a PI, or is this a pure integrator, or this combination? What is this? We write some equations. Start with the model. The model has a model transfer function, the well-known b1 z to the power of -1 divided by 1 plus a1 z to the power of -1. This leads to an algorithm equation xm of k. The xm of k coming out of the model here. The xm of k is calculated with b1 times y of k minus 1. Note that the z to the power of -1 in the numerator delays the input signal of my model with one step, minus a1 x model one step before. This is the denominator coefficient. The a1 can be calculated, the well-known equation e to the power of minus sampling time divided by time constant. b1 is the well-known coefficient km 1 plus a1. Okay, that's the first step. In the summing point, here we can also write down the equation. Summing point equation is y of k is y1 of k, output of my P controller, y1 of k plus, and now this signal out of my model is 1 divided by km times xm of k. Okay, so far. This was a summing point equation at the time point k, but of course, one step before we have a similar situation. All k's have to be now reduced with -1. And then you see, I just make a copy of this equation and get the situation one step before. So now I solve this equation to the xm k minus 1 expression. So I bring this expression y1 on the left side and multiply with km. So this is km with y k minus 1 minus y1 k minus 1. Okay, and this is then used in this equation. You see, replace by replace, I have now xm of k is b1. b1 is km 1 plus a1. I copy now this equation in this line and replace b1 with km a plus a1 times y of k minus 1 minus a1 times xm. Now I replace xmk minus 1 with this expression. It's a1 times km y of k minus 1 minus y1 k minus 1. Yeah. Could ask, what should this expression brings for new information? You will see. You will see. Wait for a moment. We are just in a few steps. We are ready, and then you see. This is really great. Yeah. Wait for this. Strange fill and backwards fill and so on. Now I go with this xm of k. Now with green arrow, I go to this point. What happens then? Okay. I copy this line. Y of k. Y of k is y1 of k plus 1 divided by km multiplied with all these what I have in the right part of the last equation. So km 1 plus a1 times y of k minus 1 minus a1 km y of k minus 1. Strange. I think this is really strange, but look what happens. Y of k minus 1. Parenthesis closed, parenthesis closed, parenthesis closed. So, what is the result? Okay. What is the result? Y1 of k is unchanged. You see the 1 divided by km reduces this km. All these expression is multiplied with km, and this km is also a factor for the complete right expression, so km is gone. Then we have plus 1 times y of k minus 1. So plus y of k minus 1 plus a1 y of k minus 1 minus a1 y of k minus 1. So we can say this a1, let's do this in blue, this a1 times y of k remove this y of k minus 1. What is the last expression, which is a result, is 1. Now 1 times, this 1 times the y of k we have covered, minus a1 times minus y1 of k minus 1. So we have a plus a1 times y1 k minus 1. Okay, to see that this is a PI controller, we replace now y1 of k with a sub o times control difference of k. Note, yeah, y1 is a sub o, y1 is a sub o times control difference. This is xd. So y1 of k is a sub o times xd of k, and y1 of k minus 1 is a sub o times xd of k minus 1. So we have finally the following expression: y of k is y of k minus 1. The old output, new output is old output, plus a sub o times control difference of k. Yeah, y1 is a sub o times control difference plus a1 small lowercase a1 times uppercase a sub o times control difference k minus 1. You see, if we have yk is coming out of the sum with a recursive term yk of minus 1, this is an integrator. And note that in a PI algorithm we have y of k. Yeah, I show you now the similarity, plus q sub o times xd of k plus q sub 1 times xd of k minus 1. So we can say, okay, very similar, if q0 is a sub o and q1 is a1 times a sub o, then we can really compare the comparison. The q0 is a sub o and the q1 is a1 a sub o. You see the a1 is negative. Note a1 is negative, so that's good, because if both are positive, we have just not a real PI controller. Now we see that the q1 is a little bit smaller. q0 is negative smaller because a1 is a number which is smaller than 1. Then we can say, okay, note in our PI design we have a kc 1 plus t sub o divided by tn, and this is negative kc. So we can say, okay, if we compare the PFC, now that is the PFC, with the PI, we can say, okay, the integration part is the same, but here we have a q sub o, which is our factor a sub o. So if we compare this, you can say, okay, this is nearly the gain plus this small integration factor. We can first see the sum of both elements gives us an indication of the integration time of my PI controller, the PI time constant, and the Q1 is the negative Kc. I think this comparison is not so suitable. We can say a better comparison with the Baumann version. Note Baumann PI. If you look into chapter 6, then you can see Q sub O was Kc and Q sub 1 was Kc multiplied with minus 1 plus dO over Tn. That was the second possible version. It's very similar in the behavior, but now we can, for this, we can now see what it is better. So Kc is A sub O, and this gives then A sub O times 1 minus 1 plus sampling time divided by Tn, by the time constant of my PFC. So we now can say, okay, this must be A sub 1, A sub O. So we have now a good equation for A1. A1 is negative 1 plus TO divided by Tn. So we can say, okay, the PI controller has a gain Kc, which is identical to our A sub O. A sub O was Yeah, A sub O, note the calculation with the lambda factor and with the DC gain of the controller and so on. This was the expression developed in the PFC theory of Mr. Richalet. Depending on the A1, the process gain, and this lambda factor containing the 5% settling time. So the design of the controller delivers a controller gain which contains information about the 5% settling time. So I think that's interesting. Normally we design a PI controller with border plot design. In this case, the design works just by asking the user of his 5% settling time. So this has a nice feature. Yeah, this is a nice feature. And the time constant also is automatically coming out of the process time constant. The A1 is nothing else than e to the power of minus sampling time divided by process time constant. If you compare this, then I have done this. Tn over T sub O, you can solve this. If you want to know how large is the time constant of my PI controller, I can solve this equation to Tn, which is Tn over T sub O. To over T sub n is 1 plus, oh, this must be negative. Sorry, there must be a negative sign. Quickly change it, is minus. So this is 1 minus e to the power of minus To divided by T, and Tn over To is then the inverse of this, 1 over 1 minus e to the power of minus sampling time divided by process time constant. If you compare this, I have made a table by using different versions of sampling time over this time. I just put this picture near to this equation. Yeah, sorry, wait. Yeah, in the paper you can find this table. I use now different values T over T sub O and write it down. So from 1 to 100. And with this expression, I calculate now Tn over T sub O. And you see this is if the ratio of time constant over sampling time is 1, here you get 1.58, but I think starting with 5 or 10, yeah, that is the normal ratio. Yeah? Process time constant divided by sampling time should be 10 or larger. Here you see that the theoretical Tn of my PFC is nearly identical to the process time constant, and we call this pole compensation. Yeah? That is nothing else than pole compensation. So we can say PFC is a PI controller. Design doesn't need FRA method also. User gives 5% settling time, and Tn is selected with pole compensation. And furthermore, an anti-wind up is automatically included. Yeah, this picture, we cannot see this, but if y of k is limited and held constant, then this part, this integration part, cannot run away. That is a very nice feature. By limitation of y of k, the value of y of k, or there is no internal integration part which runs away with the wind-up effect. So automatically this includes an anti-wind-up mechanism. So the PFC is behaving like a PI. The design is nice, and anti-wind-up method is automatically included. That is the result of this chapter, and yeah, I like it.